Hi folks, we are on the Unit 3 Day 7 lesson, and today we're talking about the intersection of two planes. In the previous work we looked at how lines could intersect either with another line or with a plane, and today we're talking about how two planes could intersect. So we've taken kind of lines out of this situation and are just looking at the relationships between different planes. So we know that a line could intersect a plane in a point or not at all if it was parallel, or in an infinite number of points if the line actually lay on the plane. We're going to look at the different cases for two planes interacting. So the first situation here, we have the intersection of two planes, and our first case is probably the one that you think of most often. If you held up two pieces of paper and said, how could these intersect each other if they were planes in space? You would notice that if you put those two pieces of paper together, you will get a straight line where they would cut through each other. So two planes are not going to have a point of intersection. If they intersect, they're going to intersect along a line. And that would be case one. And that's kind of the typical case that we likely think of. There's two more cases though. So in case one, the solution is a line, so it is an infinite number of solutions, but those points follow the specific equation of the line of intersection. So there's no point of intersection of two planes, but there would be a line of intersection. The next case here would be if we had two planes that were parallel. So in this case, we've got two planes and they will not intersect at all. The way we can recognize two parallel planes is by looking at their normals. So just like with the intersection of lines and planes, we are going to need to have the equation of our planes in Cartesian form. If you're given the equation of a plane in vector or parametric form, you have to convert it to Cartesian using that cross product skill. So here we're going to have the normals will be scalar multiples of each other, but the equations of the planes, when they're put in standard form, will be different. And the way we would identify kind of the converse of that, if we were looking at case one, the normals would not be scalar multiples of each other. Those two normal vectors are not going to be parallel. So again, in case two, we've got no solutions because our planes are parallel. There are no points of intersection. Case three is the case where there's two coincident planes. So the normals will be scalar multiples, or actually the same, and the Cartesian equations will be the same as each other in standard form. And that's one reason why it's really important to standardize that Cartesian equation and how we write that out by eliminating fractions, by putting that first term as a positive and reducing it to lowest term, so we can very clearly see if these are equal. So again, these planes are coincident. There's also an infinite number of solutions, but here it would be all points on the plane. So case one and case three both have an infinite number of possible solutions, but in case one, it's the infinite number of points on the line of intersection, and in case three, it's going to be all of the points on the plane. So case three is slightly broader definition of the infinite number of points. We would have to include all of the points on the plane, and in case 1, you're still going to have an infinite number of solutions, but you have to define it as the points on that line. So we're going to take a look at a few examples.